Okay.
I went last Monday. It was empty. You guys should get prison tickets for next week. Yeah. Next Monday, I'm going to be here.
All right, good morning. Good morning, everyone. Sorry I'm a bit late. One of the kids got sick, you know. Anyway. Oh, thank you for coming in droves. This is the worst morning to come here. It's dark, it's wet, it's cold, yikes. I mean, I'm from tropical country, so anywhere below 20 degrees, too cold for me. Yeah, anyways, so we're at chapter 8 now. Chapter 8 is easy. It's not interesting in teaching you chapter 8. Well, there are problems that I selected that I think are relevant to whatever that has the chance of appearing in the exam. And as if you can see, I don't know if you had time to glance over because I just sent it last night. The problems are mostly just applying formulas. So take your pen and paper and then write these formulas with me. There are some explanation as to how those formulas come about. I'm going to explain it in some details, but if you take a look at these lecture notes that I put, there are some derivations of those formulas. You're not going to be asked to derive anything in the exam. The goal of the module is to allow you to use these principles, but not to derive them. Well, how about the first formula, Reynolds number? But before that, I want to recap a little bit about what you've studied so far. Time flies, isn't it? The first chapter was about viscous flow. You know everything about shear stress, about viscosity, about its effect on the flow when solid and fluid are in contact with each other. And then you forget about that for a while in chapter 2 and 3. In chapter 2, you deal with how pressure varies according to heights or according to depth. And then chapter 3, you deal with ideal flow. And these are Bernoulli's equations, continuity, and all that. Anyway, now all of them come together in this thing. Viscous flow in pipe. Now, if you have a flow in a pipe, so chapter 8 is really for chemical engineers. And there's a reason why you're not studying chapter 7 or chapter 10. Some of them deal with external flows. So those are for aerospace engineers. But you deal with internal flow. That doesn't mean the flow happens indoor. That means that the flow takes place in a pipe. It's in a pipeline, in a pipe, in a valve, anything that is contained. That is contained, anyway. So if you have flow in a pipe, that's your pipe, all right? There are many ways by which the velocity profile look like in a pipe. If you take a look at the faucet in your kitchen, and then, in the morning you open it and water starts pouring out from the faucet, you see that at some point, when you don't open it big enough, it flows rather uniformly. Like this, for example, right? Like the one you observe in orifice plate when it's steady. You notice that, there are some order in this. You can always see it as something that is still, right? It's almost not moving, it's steady state. This region, as the flow just come out of the orifice plate, is what we call laminar flow, generally speaking. And then, somewhere downstream, if you allow it to fall far away enough, things start to become disorderly, right? And, you see something like that. You see that everywhere. Generally speaking, this is an illustration of flow transforming from being laminar to being turbulent. Now, I cannot stress you enough how important this is in terms of looking at these two flows from different lenses. As a mathematician, or as a scientist, or as an engineer, when the flow looks like this, almost everything here can be described from first principle. You can derive, for example, how the flow profile looks like just by using Newton's second law. Just like what we've been doing in the first 3 chapters. But when the flow becomes turbulent, nothing, even until now, people has been able to describe that. What I meant is this. If your flow becomes turbulent, and then you want to find out at any depth, for example, that depth, okay, at that depth, what is the velocity? No way to find out precisely. No way to find out precisely. So what do engineers do? Well, they run experiments. They run a bunch of experiments, and then they average those results, and then take a guess. It is like that. Now, when the flow is still laminar, it's different, provided that it's perfectly laminar, yeah? Laminar. Any place here, there, you want to find the flow profile here? What's V there? V3, V1, V2. You can tell, even without going to the laboratory. You can tell. And the lecture notes will tell you exactly how to do that. Now, in terms of flow in a pipe, the most important thing in the exam would be to know when the flow is laminar and when the flow is turbulent. Well, you can tell. Well, that's kind of laminar. Everything is orderly. It looks as if the flow is frozen. And this looks disorderly. The diameter keeps changing. Fine. But when it's in the pipe, you cannot tell when the flow is in what regime, right? So there is one method to do that. It's called the Reynolds number. Now this you have to memorize. Reynolds number is a non-dimensional number. That means it has no units. It means the number isn't followed by anything. Meter per second, nothing. It's just a number. Now that number is a ratio between inertial forces. So that's the definition, so 3 lines. Inertial forces and viscous forces. So that's roughly what that number is. Inertial forces, viscous forces. That thing is so philosophical that even if you are, I think, and I hope some of you decide to do PhD one day and to dig deeper into this. These two forces, like good and evil all the time. It's like yin and yang in Chinese culture, folklore, or whatever. I think it manifests in different ways, but quite similarly in all cultures. This one is chaos. This one is order. This one, keeps moving uncontrollably. This one dampens things, slows things down, make it orderly. All right? Now, the most beautiful thing in physics is that you can actually put the formula in, so you know the number exactly. It's not just, this is, enlightenment or anything like that. So, rho u d. That's inertial forces. And then the other one is mu. You know about mu. Mu is viscosity, right? And rho is density. U is an average velocity. And d is the inner diameter of the pipe. So that's your d. That's d. Okay. And, well, I don't draw you the U profile first because I don't know if it's laminar or turbulent. Okay? And rho. Okay? Now, you have to memorize this. You have to memorize this. There are many variations of this Reynolds number because you can change absolute viscosity into kinematic viscosity if you want. Or you can change U into volumetric flow rate if you want. What else? You can change it into mass flow rate too if you want. But that in general is what you have to memorize. So if there's any question in the exam that tells you, what would be the kind of number or parameter that distinguish two different flow regimes, you say Reynolds number, and then explain all the terms. Well, you explain all the terms, and you tell me, what these parameters actually mean. Yeah? Okay? Now, for example, if you want to change it into another form, I think the other variation would be U d divided by kinematic viscosity, like that. It's a ni. It's a Greek letter, ni. It's like a V, but drunk and slanted left. So that's kinematic viscosity. Or you can express this in terms of volumetric flow rate, and that will make it Q d over, well, obviously volumetric flow rate calls for area. Or you can simplify it into 4Q, whichever one is shorter, I think, d, something like that. Given that volumetric flow rate and mass flow rate is actually connected, don't worry, I'll slow down, I'll repeat this again. Hang on. Oh, I could do this. What is that? No, that's... What's that? Oh, well. That doesn't make sense. Where's this camera facing? You see? See that guy? It got stuck. Good thing I bring my own camera. I knew it will happen anyway. Yeah, whatever. Now, what I said before, because Q and mass flow rate m dot is connected, well, you just multiply it by density, right? Given m dot equals density mass flow rate, F, volumetric flow rate, then this guy can be 4 m dot divided by, this isn't really interesting to explain because it's just formulas after formulas after formulas. Well, I don't like memorizing formulas, so I won't. At least I won't memorize all of them. I think this is the only thing I will memorize. And make sure you memorize it. Always. You can change it into anything, right? Let's say the problem tells you, instead of U, the problem tells you, well, there is a flow in a pipe, the volumetric flow rate is something. Calculate the Reynolds number. What are you going to do? Well, you have to apply this relationship, right? And then you get the U. And then you get the U, you multiply it by D, divided by this. Or you can memorize it like this. Then you don't have to change this into that. Whichever way is easier for you. If you got a photographic memory, bam, okay, that's great. I doubt it. You might think you have, but no. Anyways, so any questions so far? Let me give you an example. A really quick one. Oh, no, before that, hang on. Before that, what about if the flow is in a pipe, but the pipe isn't circular, cross-sectionally speaking? That's a sensible sentence in English, right? Yeah. Like the air ducts. No, who needs them, right? Yeah. Anyway, in old buildings you have air ducts, and usually they're rectangular. Then what would the diameter be? There's no diameter in rectangles. So this is what you do. You have hydraulic diameter instead. Hydraulic diameter, and that's, well, dH, just to make it different than H, is 4A, which is area, divided by, this is called wetted. Perimeter. So all I'm saying is this. If you got a rectangle instead of a circle, like that, okay? Well, obviously the area, you know what? Actually, this not need to be just for rectangle. It could be for triangle if you want, or hexagonal, any shape really, so long as you can find the area, yeah? So if the cross-sectional area of the pipe through which your flow takes place is nothing is other than circle, then A is the area and P is the wetted perimeter. Now, wetted perimeter depends on what fluid flows through it. If it were gas, obviously gas fills the room, right? And then so everything is wetted because it fills the room. Like in this room, for example, all the molecule of the air touch the walls and the ceiling and the bottom. But if this room is filled with water, for example, well, it won't touch the ceiling unless the room is full with water, right? So if it were filled with water instead, maybe, it could be some certain depth. Yes? In that case, the wetted perimeter is only the length from here to here to here. Okay? If it were filled with gas, which fills a room where it's contained, then the wetted perimeter would be just the perimeter of the entirety of the cross-sectional area. That would what P be. Okay? Okay? Now, Area is area, period. So, I could change that into this if I want to, and that would what your memorized formula be if you want. Well, you might ask, what about if it's circle? Well, if it's circle, then if this were circle, for example, yeah, you will notice that DH is 4 multiplied by what's the area of a circle? Pi. Yes? And what would the perimeter of a circle in terms of diameter? Yeah? Your voice is not commensurate with the size of your body. Yes. Yes, circumference of the... Exactly, great. That's all right, gentle voice. Yeah. Okay, I can cancel the whole thing. Not the whole thing, but you know, the pi, the 4, and the d. What does that reduce to? D. Yes? So you know that hydraulic diameter reduced to d for circle. Well, then I could just replace that with dh if I want to. All right? So that's that. Yeah? Any questions? Yeah.
For the A in the first equation.
Okay.
Yeah. Is that the cross-sectional?
Yeah. The cross-sectional area resulting from D here. Yeah.
Is it the wettage?
No. Just the area. Just the area. Okay. Only, this is just the area. And P, by definition, is wetted perimeter. Here's the thing. And the reason why that might not make sense. Originally, Reynolds number, if you're interested in the derivation of it, the formula was rho u characteristic length divided by mu. Now, you will study flow in porous media in year 2 or year 3, I'm not sure. Porous media flow is flow that takes place in a pipe, but through rocks or through marbles or through complex geometries or bead packs, which is ever present in the battery industries, right? You know, the ion has to go through, in a fuel cell, for example, the ion has to go through porous media. Now, in that case, the characteristic length no longer is the inner diameter. The characteristic length becomes the grain diameter. This thing can be anything. And in fact, it is still a subject of a debate. What should I put here? This is really engineering world. Engineering world does not talk in certainty, unlike math. Math talks in certainties. Engineering talks in, well, does it make me money or not? Really. In the end, it's about that. All right? So I cannot explain to you why this one is not wetted and this one is wetted. That's the consensus in the engineering community. So, all right? So now we know Reynolds number. We know hydraulic diameter. We have one equation for you to memorize. And then there is this concept about entrance flow region. Well, let's make this longer. Now let's say this is a pipe attached to a container, like a tank, for example. Right? That's the tank opening. Right? That's a tank here, right? And then there's a valve. You open the valve, and flow starts rushing in. Okay? Now, what do you think happened to the velocity profile? immediately after the valve is opened. Okay, that's the pipe, just to make it clear. Do you think the velocity profile will immediately look like a parabol? No, it doesn't. Because the viscous forces hasn't had the time to take effect yet. So immediately here, flow looks like what Bernoulli flow looks like. Because viscous forces takes place when fluid is in contact with the solid, right? And there's not enough body of liquid in contact with the solid yet when the valve just got open. So flow looks ideal like this. Like that. That's what flow looks like immediately at that point, yeah? The point is where the arrow originates. The point is not where the arrow ends. This is the point, okay? All the flow here looks like uniform. Why? Well, because there's only a little area here where viscous forces take place. And there's not enough time for viscous forces to creep into the center of the flow. Now, but as flow takes place along the pipe downstream, viscous forces starts to creep in. You see these molecules holding hands with the other molecules? They start to, no, don't go too far. Don't go far yet, you know. And then immediately this guy holds hand with that guy, this guy holds hand with that guy, and immediately everybody tells everybody not to go too fast. That's what happens. So, if you take a look at somewhere downstream, you know, maybe the flow start to look like this. Okay? That means from the molecule here until the molecule here, they already know that this guy here is holding hand with the solid. The rest don't know yet. Okay? Now around here, for example, finally, all the molecules know, you know, there's viscous going on. And they look like that. This is what scientists without access to experiment think about. You know, ideally, it's going to look like that. And the flow from being completely non-viscous, aviscous, or inviscid into fully viscous flow. That's viscous flow. Remember chapter 1? Yeah? Like that. Now there is a region here from here. Let me put it in red. Roughly from here to here. Not a good one. Okay. Something like that. Yeah? That regime here called inviscid core. Inviscid, it means non-viscous core. That means in that core, if I could, I don't need to do this, but make it cluttered. In this core, the flow hasn't seen viscosity yet. The flow is simply governed by inertial forces. Okay? And finally, you know, at certain length, that length is called entrance flow region. From here until there, it's called an entrance flow region. LE, length entrance. Okay. That's an entrance flow region, LE. That's very important Now it's just a definition. You might think, what the hell am I supposed to do with this information, right? That's really important. Let me digress a little bit, because your job as an engineer would be to find out, roughly speaking, energy that I need to transfer fluid from one point to another. And the length between one point to that another point is unknown. Depends on your client. And the path depends on the specification of the factory. So you need to know LE, because it has great implication to the energy required to do that. Okay, so that's the entrance flow region. Now, before we move on here, let's go back here again. Now, roughly speaking, for laminar flow, Reynolds number is between 0 to 2,000. So 0 to 2,000 or 2,200. Some books will say 2,400. Some books will say 2,000. Okay, but let's agree on the average. And then for turbulent flow, Reynolds number is greater than 4,000 or 4,400 even. Okay? You can memorize this. It's recorded, and I think my handwriting is big enough too. Now that you have to memorize. You might ask me, where do these guys get this number, and why is it so imprecise? They get it from a bunch of experiments, really carefully in close environment experiments. All right. So the way they do that is by flowing fluid through a pipe. They can change the diameter, right? And they can change the U by changing the volumetric flow rate. And then so they have many different set of data, so they can calculate the Reynolds number. The pipe is probably made out of glass, so they can tell, when the flow becomes disorderly. And roughly speaking, flow starts to become disorderly or turbulent at Reynolds number about 4,000-ish. And for definite, laminar flow takes place below 2,000. So what's happening between 2,000 and 4,000? Well, engineers say sometimes turbulent, sometimes laminar. The data is inconclusive. So your job as an engineer is not to design anything at Reynolds number between 2,000 and 4,000, because nobody has an idea whether the flow will be laminar or turbulent at that time. Little disturbance or perturbation could switch laminar flow into turbulent anytime between that Reynolds number. So just to be safe, design something either way above 4,000 or well within 0 to 2,000. All right? So that's laminar flow and turbulent flow. Remember the faucet of water? I opened that, yeah? So, sometimes it happens near the faucet, sometimes downstream, right? It's like that. So that's really unpredictable. All right. Now, that length here, the length at which flow becomes fully viscous is very different for laminar and turbulent flow. So here's another equation for you to memorize. For laminar flow, the length over inner diameter is about 0.06 Reynolds number. So that's for laminar flow, yeah? Yeah, yikes, it's like just bam, equation, eat it. Anyway. The characteristic, no, not characteristic, the entrance flow length, it is entrance flow region, the length, this length, what is it length called? Now, okay, the length is called entrance flow region, LE, divided by diameter, yeah? Divided by diameter is 0.06 Reynolds number for laminar. For turbulent, sorry, I'm going to write it here. But, so, okay, I'll write it here then. Okay. For turbulent, it is really ugly. 4.4 Reynolds number to the power of 1/6 for turbulent. You have to memorize this. There will be no formula sheet given in the exam. Luckily, that's it. You memorize it and you apply it. Well, not really. There's some thinking going on, but not much. Memorizing is thinking too. Oh. All right. Any questions so far? Can you see the, yeah? So let me repeat again. So this is the entrance flow region. Entrance from what? Entrance from a container. Now, when flow starts to take place from the entrance point, it hasn't yet feel the effect of viscosity. Over time it will, as it flows downstream. Now, there is an entrance flow regime that characterizes the length before flow becomes fully viscous. That's viscous flow then, right? It means every molecule in that flow has felt viscosity effects. Now that length is different for laminar and turbulent. And how do you know laminar from turbulent? You know it from the formula, Reynolds number. So quick exercise. Take your calculator if you have any. If not, then use your phone. Water in 1-inch pipe flowing at velocity average 10 feet per second. Calculate Reynolds number and calculates the entrance flow region. Go. When I get Kit Kat at 12 o'clock. Is the question clear? Water in 1-inch pipe, 1-inch pipe diameter. That 1-inch pipe means the inner diameter of that pipe is 1 inch. Okay? Flowing at average velocity 10 feet per second. You have no idea how it looks like. Laminar, turbulent, no idea. What would the Reynolds number be? And what's the corresponding entrance flow region? Yeah.
What's the viscosity of water?
Okay. It's about, okay. Okay. That's 10 feet per second. You can check it online, sorry, but, you know. So, kinematic viscosity of water is about 1.2 times 10 to the power of minus 5 feet square per second. Yeah? That's of water. Let me check it if it's right. Because it's in non-SI unit, I might be wrong. Water viscosity. This one is with millipoise, which is exactly okay. So in SI is 0.001 Pascal second. Okay, in feet. Okay, there. 1.2. Okay, certainly viscosity depends on temperature. Now, in the exam, temperature is at this point is not going to be mentioned. If you check Google, well, it depends on the temperature. I think room temperature is about, I don't know, in Fahrenheit, 60. A bit lower than body temperature, which is 90 something. So it's about 1.2. The dynamic viscosity is this one. Okay? Anybody got the number already? What would the Reynolds number be? Reynolds number is UD divided by kinematic viscosity. So that will be what? Go. That's the point. I don't know. The Reynolds number will tell you. You know it from the Reynolds number. So that's why you have to calculate it first. Anybody got the number already? Yeah. 69444. 69444. Good? Okay. Well, in the lecture note, it's about 68870. Fine. I guess you use, I don't know, different rounding. Okay, fine. But that's okay. 69. People get it the same? Yeah? And then the question is, so what regime is the flow in? Huh? Laminar flow is between 0 to 2,200. Turbulent flow is above 4,000. So this is turbulent flow. Okay? So that flow is turbulent. All right? Now, so calculate for me the entrance flow region for that flow. What's LE? Go. In feet, please. Well, you need a bit more sophisticated calculator. Okay? You get it? Okay. No, I don't expect you to convert any way you feel comfortable. Now, first of all, even if you do it in meter, it should give you the same number. Because this one is non-dimensionalized. Right? If you change everything into SI, including the velocity and the diameter, this number will still be the same. Has no unit anyway. The entrance flow region will change because it has feet or meter, right? So, okay. So, entrance flow region for turbulent follows this. Yeah? You need a bit more sophisticated calculator, and that would get you 4.4. Where's 4.4 come from? Oh, from there. Okay. 69 to the power of 1/6 multiplied by diameter. And in feet would be 1 inch divided by 12 feet. Okay? That will get you about 2.35 feet. Okay? It's about that. Now, anybody confused as to why this formula is used instead of the other one? Because the flow is turbulent. And how do you know the flow is turbulent? Reynolds number told you so. All right? Using that rule of thumb. Now, so it's 2.35 feet. It's almost like 1 meter long, right? So this is almost like a very like-for-like image. It's about that long, really. Well, for diameter 1 inch, so it's about, okay. So if the diameter is this small, it will take that long for water to reach fully viscous flow, okay? It's going to be like there. I think this is about 2 feet. All right. Okay, another one. Now, you got to be quick this time just to make sure that you know how to calculate it very quickly in the exam. SAE 30 oil. 1 inch diameter. U 2 feet per second. Viscosity kinematic 4.5, 10 to the power of minus 3 feet square per second. What's the Reynolds number? What's the LE? Go. So it's almost, yeah.
If the random number was between
Yeah.
what formula would you use, or does that never happen?
You don't know. So I don't know how to answer that. Nobody does. Because the flow is unpredictable. It's very engineering, right? All right, now it's oil. Similar diameter, 1 inch. Twice as fast. Is it twice as fast? Yeah, it is twice as fast. No, it's smaller. Okay. So only 2 feet per second as opposed to 10. Viscosity is considerably higher. What's the Reynolds number? Anyone? 37. Perfect. Got 2 Kit Kat. 37. Now, very quickly, is this flow laminar or turbulent? Loud. Really loud. Good morning. Laminar flow. Laminar flow. So calculate me the entrance flow region. For laminar flow, what formula will you use and what's the number? Yes, it should start picking on you at some point. Anybody? Yes. Yes, exactly. You're not looking at the lecture notes, right? Calculate, yeah? Okay, so it's about 0.06 multiplied by Reynolds number multiplied by diameter. And that will get you, like what you said, 0.185. Was it feet or inches? Feet. So it's about 2.2 inches. So it's about that. Yeah? So it's about this. It takes only that much length for the flow to become fully viscous. Now, that length, that feeling, when it comes to that in your real engineering practice, you probably just get it. I have a little hobby. I play with analog photography. So, in the dark room looking, like romantic and all shit. But, so in camera, to get the right exposure, you need to know the opening of the lens and how long it opens. Right, that determines how much light get into the film, right? And then, the opening of the lens would determine the depth of focus, right? The right bokeh, they call it. It depends on how big you open the lens. There's a formula to do that, and you have to read the light. Over time, though, you can just look at this is about, what opening corresponding to what seconds. Similarly with this, you will get that feeling, all right? There is a room for feeling in chapter 8, because if in the exam, you get, for example, instead of 37, you get 45. First of all, it depends how you get 45. But there is a lot of margin of error. You still get 100. Like the actual number in the lecture note was before 68,877. As I calculated it. And he came up with 69,444. That's like over well, not really. It's about almost 1,000 different. 1,000. He'd still get 100. You see? So that's why, that margin of error, that's why in different books, I don't know even in that book, whether it's 2,000 or 2,200. Some book says 2,100. Some book says 4,000, 4,100. You don't know. There's a lot of margin of error here. Okay, so don't worry if your number is different. That's fine. Okay, good, 1 hour mark. 5-minute breaks. Yeah? Five-minute breaks.
I feel like that video just explains.
If we have to. Sorry.
Sorry. Hey, where's my boy Luca? Over. Hey, so. Yeah.
You're talking about what glasses?
Yeah, Luca. I don't know how many there are, but yeah, Luca, the
Tall.
the extremely poised guy who seems to get everything.
No clue.
No clue. Hey, Thomas, so you can pick the dignitaries, yeah? Is Leia here? Do you know how she looks like? Yeah. Is Leia here? Leia Wharton. Well, Leia, I've been slacking.
If you want, I can message Luca.
Oh, you know?
Where he is. I don't know where he is.
No, I don't need her being here now. I just need him to know how she looks like because they will pick him up together. Thanks. Nice bread. Nice looking bread.
The mock that we've got, is this just to see how the semester's gone?
The mark
The mock
that you get,
test.
the mock test. Oh, okay. Yeah, it's just going to be, so that will be next week, by the way. I'm going to announce it. It's just, yeah, you don't have to, it's not obliged, it's not a compulsory thing, but it's just to give you a sense of, you know, this is roughly what the exam is going to look like and how long it would take you to solve it.
For January.
Yeah, you will be given feedback, all right, but it won't affect any of your grades.
Cool, because I was planning on doing all of my revision for tests during the break because I've got one.
That's fine. That's fine.
Anyway.
Just get a.
Yeah,
it just,
I'm still going to do it because it seems helpful.
yes,
Thank you.
I think it certainly will. Yeah. All right, everyone, go back to your seat. Got a lot of things to cover. So, yeah, go back to the seat slowly. You can make this a living. So I made that easy for you. So that's the distinguishing catch. So that's laminar and turbulent. In terms of Reynolds number and entrance flow region, another thing that distinguishes the two is supposedly the pipe is made out of glass and you can see how it looks like. Hang on, it's made out of glass, but it's water. Water is transparent. What am I looking at? Well, typically people use tracer, dyed fluid that got injected into a stream of water so that it can tell you basically what the streamlines look like. They do that. In the book, you'll find that one. Anyway, but suppose you can see all the vector velocities. What would laminar flow profile would look like? Well, like what you've always seen. Looks like a perfect parabol like that. It's going to look like that. And nobody can tell what's turbulent look like, right? It's just going to be like hot mess like that. The vector is, tortuous like that. Now, but if you were to average the x vector, because all of this has many different vectors, right? This vector, that vector, yeah? But if you were to only average the x vector, which you can do, pick any of this stream, just analyze the x. And then you average those x. It will look something like that. Like that. If we can see it in the lab, that would be great, but there isn't, right? So, what's the difference? The difference is that, well, as you can see, flow is very well distributed. Almost every point has very different flow velocities, right? That one is completely zero. That one and this one is completely different in length. But this one, there is a very steep change of flow near the solid surface. But then everyone else is somewhat similar. So there is a very steep change of flow velocity for turbulent flow near the interface between fluid and solid, like that, sharp, boom. And then after that, all the velocity look kind of the same. Unlike the laminar one. And then so another thing that you can put as a formula here for you to memorize is this. This is, for laminar flow, the maximum U, right? The one at the center. Yes? The one at the center in a concentric pipe should be the one furthest away from the solid. Obviously, it feels the least of viscous forces that tries to hold it back. So obviously, it is the biggest velocity. Now that biggest velocity, when compared to the average velocity, for laminar becomes two. Meaning, if you were to average all these vectors, okay, compare it against the maximum velocity, that maximum velocity will be twice as big as the average velocity for laminar flow. That's why I drew it always like a very sharp bullet rather than like a fat parabol like that, because this has to be somewhat geometrically representative. Yeah? It's about twice as high as the average. Now, what about this guy? Well, that's the maximum velocity. Well, put your engineering hat for a while, right? Most of the flows here is the maximum velocity, most of it. So when compared to the average, it's certainly near 1, because they're almost the same. So U maximum, when compared to U average, for turbulent flow is 5/4, almost 1, just slightly bigger. Okay? So that's another thing for you to memorize. Okay, now, it's not interesting at all, it's just memorizing. The thing is, how can we predict velocity in a pipe? How can we predict velocity in a pipe? So the question becomes like this. Your client comes to you and say, I want to transport things from one point to another point. It could be 100 meters away. Now I got a budget for a pump. The pump is only that much in power. The pipe, probably that much in diameter, all specified. Can you tell me roughly how much the volumetric flow rate going to be? It's a fair question, right? As an engineer, your boss comes to you, say, here's the pipe, here's the pump, here's the diameter. How much flow I can get out of that if it were water or oil or whatever? Is that a fair question? It sounds like very easy, right? Comes to you and then asks that. And then, so how can we predict velocity? Now, the next part that I'm going to explain to you will tell you exactly how. So, from the first principle, you can make a force balance of a tiny parcel, of a tiny cylindrical parcel of fluid flowing in a pipe. Unlike before, we will take consideration the viscous forces now. Okay? So there will be something like that throughout the envelope of that parcel. Okay? We will take consideration of that. All right. So, if we take force balance in the x direction for that tiny cylindrical parcel of a finite length, so that length is known, L. What would it look like? Well, all right. Supposedly, it is flowing with a constant velocity. That will render the resultant of the forces 0, because the acceleration is 0. All right? Now, what are the forces acting upon it? So, pressure certainly plays a role, right? There's something pressing from there. And there's something pressing from there. Certainly, there are pressure applied onto the whole envelope, but we don't take that into consideration because I'm only caring about x. That's x, by the way. That's my x. Good. Well, there is weight, but weight is in y direction. Let's not take that into consideration. So that's it. That there are only pressure from this side resulting in force pressing from left, and there's certainly something from here pressing it the other way around. And there is shear stress resulting in something akin to a friction. So this would look like P pi r square, where pi is the radius of that. Well, force is pressure multiplied by area anyway, right? Well, if that's P, that can't be P, because, well, you don't need a pipe at all then. Everything will be the same, right? That would be P minus delta P. I don't know what delta P is. I don't know. But it's got to be P minus some difference of P, all right? Multiplied by the same area. Okay? And that one should be because of shear stress. So the balance look roughly like this. Minus, there you go, tau multiplied by area. Now the area is not the same area as that one. The area where tau is applied onto is what you've seen in chapter 1. It's the envelope of that cylinder, right? Not the cross-sectional area, the envelope. Because that's where tau, which is actually F tau multiplied by A, right? That's F here. Of Fr, maybe, F friction, something like that. Okay? It's the envelope. And the envelope is 2 pi r, which is the circumference multiplied by the length. Got it? All right? And all of this has to equal 0. Now, long story short, I keep saying that a lot. You can cancel the p's and then maybe the pi, because there are pi's in every terms. And reordering the terms will get you delta P divided by L equals 2 tau R. You will get it like that. Let me repeat one more thing for you. Why are we doing this? Because we want to answer that question. How can we predict velocity? And how do we answer this? By the first principle. Simply by Newton's second law. Newton's second law applied to a tiny parcel of fluid, cylindrically shaped, looks like that. And that's the relationship that we get. Okay? Delta P, a hint for you, is what I meant when I say your boss gave you a pump. That pump has delta P in it. That pump has to overcome the pressure drop anyways. All right, now because you know what tau is, okay, don't get surprised. Tau in a cylindrical coordinate for that is minus mu du over dr. Well, that looks new. Oh my God. Yeah. It's not mu du over dy. It's minus mu du over dr. Simply because the coordinate change. Okay? It was before when something like this takes place. And that's why then tau is mu du over dy. Okay? But in that case now, tau is no longer du over dy multiplied by mu. It's minus du over dr. Because r now originates from here, from the center. There, y originates from the solid. There, r originates from the fluid pointing at the solid. That's where the minus comes from. I see? All right? Here, y points from the lowest velocity to the highest velocity, right? There, r points from the highest velocity to the lowest velocity. That's where the minus come from. Okay? So don't be surprised by that seemingly different formula. It is actually the same. It's just looking like that because of the... Now, here's the thing too. That's why memorizing sucks. You change the geometry, the formula changes. All right? Be really careful when you have to memorize things like your wife's birthday. So that's that. And you can substitute it there. It will get you delta P over L 2 minus mu du over dr. Okay? Divided by r. And then the equation reduces to du over dr equals minus delta P L1 divided by... You won't be asked to do this in the exam, don't worry. I keep apologizing as if it is a mistake to give you something difficult. I'm not apologizing for that. Life is tough, guys. I mean, yes, you have to know how to do this. Okay, right? So that will become that, and as you can guess, there's some integration action going on. Because if I were to change this, move it to the right-hand side, and then integrate it, I can get many things. Now, I don't want you to spend time solving that. All I want is for you to know where this comes from. Okay? If you solve this one from 0 to r, from 0 to r, yeah, if you solve this integral, which you don't have to do in the exam, but if you do, you will get u equals delta p over 16 mu L d square multiplied by 1 minus, what's the easiest way? 2r over d squared. Solving that integral, which the step-by-step is given in the lecture notes, you can tell, if you want to know, you can. Solving that integral will get you u. Exactly. U as a function of diameter, delta P, characteristic of the fluid, which is the viscosity, and the length. So you know u as a function of delta P, geometry of the pipe, which is what D and L tells you, and the fluid, which is what mu tells you, because different fluid gives you different mu. So knowing that, you know u. Isn't that great? You don't have to open the pipe. You don't have to make it look transparent. You can tell. Give me a pump. Give me what the dimension of the pipe. And give me the kind of fluid you want me to flow inside the pipe. I'll tell you what the velocity. Not only that, I can tell you the velocity at every point in that pipe. Every point. It could be here, which corresponds to r equals 0. There, which corresponds to r equals whatever. And there, which corresponds to r equals capital D over 2. Right? I can just substitute those r in the right bracket there. Now, if I do, for example, for the center of the pipe, which is r equals what? What is the center of the pipe? R equals 0. What would that equation reduce to for R equals 0? The whole bracket here equals 1. Because this guy is gone. 1 minus nothing is 1. So it becomes that. So this is the maximum velocity, isn't it? Right? You may as well write it like this. U maximum multiplied by 1 over 2R d square, like that. You can also write it that way. Yeah? So what's the U maximum? That. How do you know that? Well, I just substitute little r with 0. Theoretically, the center has got to be the maximum. Yeah? So now do I answer this question? That you have to memorize. That you have to memorize this bit. I also already gave you the conditioning a little bit. That might look familiar to you, this equation. Didn't you see something like that in chapter 1? See, it's already in the subconscious. This bit you have to memorize. Memorizing. And then, well, since you know U, you can find U average, and you can deduce volumetric flow rate from that. How do you find U average? U average you find by integrating this, which you don't have to do, because I've already done it in the lecture notes. Let me erase this. It's only if you're interested. Only if you're interested. And I hope you are. Now that I have U, I can find volumetric flow rate, yes? Well, volumetric flow rate is, don't be surprised, it's not what it looks like before. Yes, sorry. No, that's not maximum velocity. Maximum velocity is this guy. Yeah? It's not that. You know, I get maximum velocity when I substitute R equals 0, which is the center. And if I do that, the whole thing gone, leaving me with that. So that has got to be the maximum. All right? Now, how do I know volumetric flow rate? Volumetric flow rate is actually an integral of U dA. Actually, but in chapter 3, all U is the same. All U is U average anyway, right? The flow looks like that. It's all the same. In that case, in chapter 3, it reduced to U average A. That's what that solution, it's not even similar. It's exactly that. Okay? Those are two are the same. Only this bit you encountered in chapter 3. This is the actual OG. All right? That's applicable for any shape, any U. If you put U, which you just derived, onto that, and you solve the equation, which this lecture note will tell you how to, if you're interested, you will get Q equals, make it easy, pi R2 U max over 2. Okay? You will get that by substituting this onto that integral and solve it. You will get that. Here's another thing for you to memorize. That's for you to memorize. Now, what I worry about is that you're following this, some of you get tired, and you start to lose track. What am I actually discussing now? So let me repeat. I'm trying to answer this. How can we predict U if I tell you what the pump, geometry of the pipe, the kind of fluid? Answer. Bam. How do I know that? From Newton's second law. in x direction. First principle. Now, once I get U, I will want to get volumetric flow rate. Why? Because on the actual field, nobody's going to give you U, like in a formula like that. Right? Your boss won't give you that, even if it's Chinese. Right? So he will give you Q instead. Why? Because it's just one number, Q. This one is not just one number. Right? Okay. So now I get that, which is a function of still this. Beautiful, right? Okay. So knowing this relationship, then I can tell U average then. Right? Because this one is U average A. So U average is delta P D square 32 mu L. Now from that, you actually get that relationship that I mentioned to you before, but I erased. Right. Think about it. This is U max. This is U average, which is twice as big. Yes? This is another one you have to, I don't know, do you want to memorize this? Because I can derive this from this easily. Okay. Any questions? So, you see, I gave you the list of problems for chapter 8. I think the first 1/3 of that problem can be solved simply by knowing all of these equations so far. Straight to the point, applying formulas. The question might be, well, what's big D is, what is this fluid is, which means what's the viscosity, what's the length of the pipe needed for that. Yeah, it's just, once you know, is it flow, turbulent, or laminar, it's just that, you see? So this chapter 8 is not complex. Chapter 8 is just complicated. There's a big difference between the two. It's not complex, it's complicated. And start speaking like somebody from Liverpool. Understand? No. Yes, okay. Only this one on the board here, not the one before. So, what triggers me is this question. That's number one. The question which has utility is on the field, you want to predict velocity. Given delta P, geometry of the pipe, and the kind of fluid. You want to do that. And then so that, whatever derived in that red box, applies for everything. So long as this is the question at hand. Now the way we get to that point is by simply first principle. All of those derive simply from this, from that, and that alone. Okay? From that, you get that. From that, you get this. Well, you need this as well. Okay, fine. You need that, and that, you get that. You solve the integral, you get U. You solve the integral, you get Q. And with common sense, you know what U average is. So these are all just that. So like I said, I worry that you lose tracks. Okay, this is a bunch of equation. When do I have to use what, where? That's all what chapter 8 is. To know when to use what equation, where. Which rigorous problem solving will get you there. Unlike chapter 3, or chapter 2. That's a lot of thinking. Yeah, all right. Okay. Now, let's move to the second part of chapter 8. Where's my eraser? Okay, let's move to the second part of chapter 8. Now you know that the second part of chapter 8 is to know energy balance. Or modified Bernoulli. These two are the same. Again, you have a pipe. Simple, straight pipe. No fittings, no contraction, no diffuser, nothing. It's just a simple, horizontally laid pipe. You've got flow coming in and flow going out, okay? Now, you have to first identify your system. Things can get into the system and get out of the system. And what I meant is energy can get into the system and can get out of the system. That system can be made as complicated as you want. It need not be a straight pipe. It could be a complicated pipeline. It need not be just pipe. It can have pump in it, and it can have friction taking energy out of. In terms of friction, usually it resulted in heat flowing away. All right? Now, in addition to energy coming in and out to the system, flow gets in and out of the system. The flow carries within energy as well. All right? In chapter 3, bam, that's point 1. That's point 2. What do you do? Bernoulli. Right? You just Bernoulli the shit out of it. That's it. Or you put continuity, hydrostatic, put a tube here, you're all set. Now, the game changed slightly because you have viscous effects, which Bernoulli originally cannot account for, but now can because you modify the Bernoulli. So how do we modify the Bernoulli's equation? Well, just by adding terms and into it, right? The Bernoulli will look like P1 rho G plus U average square, right? 2G plus Z1, that's U average 1, equals, I make it far away for a purpose, two square 2G plus Z2. Now remember this, because this is another very important step you will get asked in the exam. Should problem like this occur? Which it will. That's the whole point of fluid mechanics, to be honest. To do this. Fluid mechanics year 1. Okay. That's unmodified Bernoulli. All right. How do we modify it? And you know what this is? This is static head. This is kinematic head. That's elevation head. These three are heads. All right? So we're talking about energy getting into and out from the system in terms of heads, which is nothing other than energy per weight, really. Okay. Now, in this system, there might be friction. Sometimes it's called head loss, HL. In this system, you can put a pump. So that's number 2. You call it H pump, right? In that system, you can put fittings, which will contribute to loss. So I'm not gonna write it down because it's going to be embedded here. Fitting means friction as well. It's just a different kind, okay? Now, in terms of putting pump, you put energy in the system, yes? In terms of friction, energy leaked out from the system, all right? So in terms of pump, you add energy into the system. Add energy into the system, right? And in terms of friction, you lose energy. Minus. All right? Now, that's number one modification. There is something into the system, usually in the form of a pump. And if that's the case, you add something into the left-hand side. And there is losses due to the fittings and due to friction. And if that happens, you put another term, but this time with a negative sign. That's one modification to the Bernoulli. Another one is this. Put an alpha there. Because in the Bernoulli, flow looks like that. That's U average in Bernoulli, yes? Here it doesn't look like that. You know, it either looks like bullet like that or something like that with very, you know. Anyway, it doesn't look like the top, right? That's why you put alpha here to compensate it. So that you can still use U average just like you did in Bernoulli. All right? Those are the two modifications that needs to be put in there. Yes? Fine. Alpha is just a correction constant that you put in the modified Bernoulli so that you can still use U average. Simply because in the original Bernoulli, flow looks like that, which is no longer the case. So, how do I justify using U average while the flow look like that? Yeah, I put an alpha in there. Now, too bad I erased this. Now, alpha for laminar is 2 for laminar, which kind of makes sense, right? Given the ratio between U max and U average. Remember that? And for turbulent is about 1. Not exactly 1, but it's about 1. So in terms of turbulent, that alpha is as good as gone then, because it's just 1. Okay? Let me repeat again. Now you have a new energy balance. Now with this equation, you can solve the whole chapter 8. Well, the complexity from this might be, well, what's U average there? Okay, and that's where all this equation is for. Yeah? And I don't know, maybe I want to be fancy and I didn't tell you what P1 is, but I stick a tube there, which I can, right? Then you know what P1 is from the height, maybe, all right? Or maybe now the question is, all right, I know all of this, and later you will know how to calculate the losses. What's the pump required? Well, you get that from these equations reordered in the way you want it to solve your problems. All right? Now, this equation is to be memorized, but not just blindly. All right? It needs to be memorized in terms of energy into the system, energy out of the system. There might be problems where there is no pump. For example, you want to flow water from a container up in a mountain, downstream, down mountain. Do you need a pump? No, gravity will do it. There is no HP, there is only losses. The question might be, well, how high should that container be to maintain a specific U velocity? I can make so many variations, and that's why there's 100 or so problems in chapter 8. Just from this. Any questions so far? So, the modified Bernoulli is modified in two ways. One, by adding these terms for energy included in the system, and this term for energy taken away from the system. The second one is to put alpha as a compensator for the fluid velocity profile not looking like chapter 3. Alpha is exactly 2 for laminar and 1 for turbulent. How do you know things are laminar or turbulent? From Reynolds number. Get it? Now from this, do we have time for one example? No, we don't. Okay, great. Now, on the 12th, you have to come on the 12th o'clock. Don't be absent. Because now we will do this, and if you can pull it off, you're in a really good shape for mock exam. All right? Yes.
I'm struggling to see how this doesn't go to 0. Because that's diameter over diameter, which would be the same, wouldn't it? So that would cancel out.
It becomes 0 if the R becomes the actual diameter of that. But R is a variable, you see. It can be anything.
Oh, so it's not the same as the diameter.
No, it's not the same.
Oh.
Only when R is at this point, which then becomes 0.
Oh, all right.
Right? Yeah.
Just got two questions. So here, so that's the radius of the.
Yeah. So this. So that's exactly that R.
And why do you divide by 2 here?
That's just coming out of this equation. The whole derivation is in the lecture notes. So that too must have come out from the working of this integral.
So not this directly then. Like not this.
No, you cannot make sense of this without solving of the integral.
Okay.
Yeah, you have to solve it, the integral. Yeah.
Is there a specified date for the mock?
It should be next Monday.
Next month?
The mock is not obligation, it's not an, it's not compulsory.
Yeah.
And it's not going to add anything to your mark. Okay? I don't know who first, but okay.
I have a question.
Yeah.
You just in this whole lecture, you just mentioned laminar or turbulent. Why didn't you mention any of the transition stuff? Since
Yeah, okay. The transition is the flow in between Reynolds 2000 and 4000. I forgot. Yeah, that's called transitional regime. Yeah, I will make sure I say it in the 12 o'clock.
so we should consider it also for everything that has been mentioned so far.
No, because there is no answer to any of this in transitional regime. I don't know what this is for transitional regime. I don't know what entrance length. I don't know what alpha for transition. There is absolutely no information. Yeah. Okay? Yeah.
When is the exam? Like not the main exam, but the test exam.
Oh, next week.
Next week.
There'll be mock one. Yeah. Okay. Yeah. Okay.
What does this mean?
Sorry?
What does this mean?
What does what mean?
This one.
16.
Oh, okay, I thought it was LB.
No, 16. Yeah. 16. Okay. So, one moment. I need to wrap things up.